All right, so with the second part of this video, I'd like to start here again at the motion paths, showing, in this case, a single dwell displacement profile. So again, we're trying to solve the problem of what these functions should be for the rise and fall, such that they satisfy the fundamental law of cam design. All right, so let's take a look at a couple of things. Most of these are going to end up being what we're going to refer to as step functions, because the cyclic motion of the cam is going to go from a well-defined function to these dwell locations. So for instance, a double dwell cam is going to have this situation where it's going to start from a position of 0 over in this case, by the way, I'm making all the intervals being pi over 2. So 4 intervals will give us the full 2 pi, or 1 revolution of the cam. So pi over 2, starting out at 0 and dwelling there for 0 to pi over 2, then rise from pi over 2 to pi. And notice that again, I'm using specific intervals. So it's the theta being greater than 0 and less than or equal to pi over 2, and then it has to be greater than pi over 2 and less than equal to pi, and so on. So then we're going to get up to the dwell, the high dwell at position H, and then go through a fall function. So what we're trying to do is to create these stepwise functions such that they produce continuous derivatives. So what we can take a look at here is a picture right out of the textbook that shows what can happen for different situations. So if we have a constant or a linear rise, which is going to give us a constant velocity, but then we reach into this situation essentially right here where the velocity has to go from 0 to some defined value in no linear, no angular displacement or no time. So you basically get an infinite acceleration, and that infinite acceleration in turn is going to produce and some what we like to call infinite jerk. So again, the step functions are places where the velocity changes, and the velocity occurs in 0 time. So here it is mathematically, delta V over 0. So division by 0 gives you infinity. So what I've done here is coming back to here. So here is the position function. Now what I'm basically doing is taking this picture from the textbook and breaking it out into actual functions. So what I've done here is the low dwell, and you can prove that I'm right. This is just y equals mx plus b, where here's my b, and the slope is going to be 2h over pi, and here is x. So I'm basically solving for this linear line such that it passes through 0 at pi over 2 and passes through 1 at pi. Then we have the high dwell, and likewise again we're going to go from 3 pi over 2 to 2 pi with another linear line. So these points here, when I plot this using the Mathematica step plot function for stepwise values, the filled circles are going to indicate real points, right? They're sharp corners, but they are still real points. Now, however, when we get to the velocity and we take the derivative of this function to give us the velocity, we find out that there are distinct discontinuities, right? We jump from a value of 0 to a value of well, if we have a rise of 1 for this particular case, my velocity is going to be somewhere between 0.5 and 0.75. So these are points that are discontinuous, or discontinuities. So what we end up again is that we are finding that at each one of the specific locations that we want, the acceleration needs to be 0, and in between each of these it has to be 0. But what we find out is that to go from this side of the 0 acceleration to this side of 0 acceleration, there had to be a point when the velocity changed. And That's what I'm basically showing over here. The velocity had to go from 2 over 2 over pi times h minus 0. So on this side we have a velocity of 2h over pi, and on this side our velocity is going to be 0. So, and we divide that, so this is a positive quantity, and we divide this by 0, again giving us infinity, but this gives us our positive infinity. And the same thing is going to go for here and for here and for here. So then once we've done that, we now also have a problem with the jerk relations, because we again have 0 jerk at each one of these locations where the acceleration is constant. But to go from 0 acceleration to infinite acceleration, that's going to give us an infinite jerk. And then to go from infinite acceleration, infinite positive acceleration, back down to 0, we have to have negative infinite jerk. So that's where these positive and negative infinite jerk go on. And I've written out the functions here, right? So for this side, the rise over the run, so the rise is from positive infinity minus 0, that was the rise, over the run, which is 0. So you have a positive infinity. And on this side, coming down, you're 0 minus infinity, and again dividing by 0, so you get your negative infinity. But nonetheless, this is a problem. Now, the textbook then goes into the discussion of maybe we could do simple harmonic motion, because the derivatives of all the cosine and sine functions are continuous. So what I'm showing again here is this function over here, this function here, and this function here are just cosine functions that are matched to these particular coordinates. So this function gives me a rising cosine function to be from pi over 2 to pi, and this function is a falling cosine function from 3/2 pi to 2 pi. When we take the derivative of this function, we get our velocity function. So you see the velocity is accounting for the position starting and then slowing down again, which is what we would kind of expect. But then what happens is the acceleration has to start out, and we get again discontinuities here, because the acceleration had to go from 0 velocity to some defined value of velocity in 0 time. And likewise, we have these discontinuities in the acceleration, which then, as we've just said, will cause infinite jerk. So we can't utilize the linear function over here. We can't just use a simple harmonic motion. So maybe there is another approach. So if we specify the displacement function, which is what we've tried to do, this has led to conditions that violate the fundamental law of CAM design. So in the next video, I'm going to look at a better approach where we specify the acceleration function, and then we have to integrate these to obtain functions for velocity and displacement. So what we're going to do is we have to start the process by identifying the required conditions at each of these junctions. Well, we're going to refer to them as boundary conditions. All right, so I'll pick this up in the next video.